13.8 billion years ago, everything, every galaxy, every star, every atom in your body was compressed into a space smaller than a pinhead. And the proof of that moment? A faint hiss two radio astronomers initially blamed on pigeon droppings caked inside their antenna. That accidental signal confirmed the greatest cosmic secret of all, how everything began. But the beginning is only the first chapter. From our solar system's birth to the dinosaurs' extinction, from black holes to the search for life beyond Earth, the universe has been hiding far more than one secret. Immediately after the initial expansion, the infant cosmos was a chaotic, hot soup of subatomic particles, too energetic for stable matter to form. As space stretched, the universe cooled. Within 3 minutes, the temperature dropped enough for the first atomic nuclei, mostly hydrogen and helium, to form. For nearly 400,000 years, this dense plasma drifted in darkness. When the temperature fell to around 3000 Kelvin, electrons bound to these nuclei, creating the first neutral atoms and allowing light to travel freely. With the cosmos now transparent, gravity began organizing this raw material. It pulled vast clouds of gas together into dense pockets, which collapsed under their own weight to ignite the first stars and assemble the earliest galaxies. The story of the universe shifted from simple expansion to structural organization. Over billions of years, successive generations of stars forged heavier elements, scattering them across space. This cosmic recycling eventually created the rich chemistry that built the rocky planets, gas giants, and our own solar system. The Big Bang theory stands as the standard model for the early universe, built on hard, observable evidence rather than speculation. 3 distinct pillars of observational data support this model. The first is the cosmic microwave background, a faint glow of microwave radiation filling every corner of the sky. This radiation represents the cooled relic afterglow of that early, hot epoch when light first began to travel freely through space. In 1964, Bell Labs radio astronomers Arno Penzias and Robert Wilson stumbled upon this signal while calibrating the Holmdel Horn antenna. They detected a persistent, uniform hiss that registered at approximately 3 Kelvin above absolute zero, regardless of which way they pointed the instrument. After painstakingly cleaning the antenna of pigeon droppings, removing the nesting birds, and eliminating local municipal radio interference, they realized the noise was not a technical glitch, but the fossil radiation of the early universe. This discovery earned them the 1978 Nobel Prize in Physics. A second pillar is redshift, Edwin Hubble's landmark observation that light from distant galaxies systematically shifts toward longer, redder wavelengths reveals that space itself has been expanding continuously for billions of years. The final pillar lies in the chemical composition of the oldest observable cosmic gas. The observed ratios of primordial hydrogen, helium, and trace amounts of lithium in deep space match the exact nuclear reactions predicted to have occurred during the universe's first 3 minutes of nucleosynthesis. The Big Bang model explains the physical history and expansion of space and time from an initially hot, dense state, establishing a rigorous, evidence-based standard for modern cosmology. It does not describe an explosion in pre-existing empty space, nor does it address speculative scenarios before this initial expansion phase. Approximately 4.5 billion years ago, a dense cloud of interstellar gas and dust collapsed under its own gravity, forming a spinning protoplanetary disk around a young star. At the center of this disk, our Sun ignited. In the surrounding disk, temperatures varied wildly, sorting chemical elements by their condensation points. Tiny dust grains collided and stuck together, gradually forming millimeter-sized aggregates. Over millions of years, These small clumps grew through mutual collisions into kilometer-scale rocks called planetesimals. Gravitational pull eventually drew these planetesimals together into planetary embryos, which swept up the remaining debris to build the 8 planets of our solar system. For centuries, this process remained a theoretical model. That changed on February 8, 1969, at 1:05 a.m., when a massive fireball streaked across the sky over Chihuahua, Mexico. The Allende meteorite exploded in the atmosphere, scattering over 2 tons of primitive carbonaceous chondrite fragments across the desert floor. Unlike Earth rocks, which are constantly melted and reformed by tectonic activity, Allende remained largely unaltered since the birth of the solar system. Inside its dark matrix, scientists discovered white, irregular patches known as calcium-aluminum-rich inclusions, called CAIs. These inclusions contain some of the oldest mineral phases ever formed in the solar nebula. In 1973, chemist Robert N. Clayton analyzed the oxygen isotopes within these CAIs. He discovered a highly specific, primordial oxygen signature that differed from any material found on Earth or the Moon. This isotopic fingerprint revealed that CAIs were the very first solid materials to condense out of the cooling gas disk. By measuring the radioactive decay of uranium isotopes into lead within these mineral packages, researchers locked down a precise age. The data placed the formation of these inclusions and the birth of the solar system itself at exactly 4.567 billion years ago. These meteorite samples turned planetary origin from a theoretical concept into measurable history, providing a tangible clock that anchors our understanding of cosmic time. 66 million years ago, a 10-kilometer asteroid struck the Yucatan Peninsula, bringing a sudden end to the Cretaceous period. At this geological boundary, known as the KPG boundary, non-avian dinosaurs completely disappear from the fossil record. In 1980, physicist Luis Alvarez and geologist Walter Alvarez proposed the Alvarez hypothesis, linking this sudden extinction to a massive cosmic impact. Their evidence began with a thin, worldwide layer of clay rich in iridium, an element rare on Earth's surface but abundant in asteroids. Further proof emerged inside the clay: quartz grains showing microscopic planar deformation features. Known as shocked quartz, these structural alterations only form under extreme shock pressures of 5 to 35 gigapascals. Those forces far exceeded volcanic eruptions. The physical scar of this event lies buried beneath the Gulf of Mexico near Chicxulub, where a 180-kilometer-wide crater marks the collision point. The impact released energy equivalent to 100 teratons of TNT, vaporizing target rocks and sending a plume of debris into space. As this ejector fell back to Earth, it frictionally heated the atmosphere, igniting global wildfires that injected 15,000 megatons of soot into the sky. Simultaneously, hundreds of billions of tons of sulfur gases and fine silicate dust rose into the stratosphere, forming a dense global shroud. This veil blocked out sunlight for months, plunging the planet into a prolonged, near-freezing impact winter that halted photosynthesis. Terrestrial and marine food webs collapsed, ultimately wiping out 75% of all species on Earth. While massive volcanic eruptions in India, known as the Deccan Traps, were already releasing climate-altering carbon dioxide and sulfur gases, they acted as an environmental stressor rather than the primary cause of the collapse. The Chicxulub impact remained the main driver. Within a geological blink of an eye, the dominant life forms on Earth vanished, demonstrating how quickly a stable planet can be transformed by cosmic forces. The departure of the woolly mammoth from the prehistoric record followed a slow, staggered path. Toward the end of the Pleistocene epoch, rapid warming transformed the highly productive grassland known as the steppe tundra into wet, forested terrain. This environmental shift restricted the mammoth's specialized feeding grounds, forcing populations into increasingly isolated pockets. As these large herbivores struggled with a shrinking environment, expanding human groups added further pressure. Archaeological evidence shows that hunters targeted these stressed herds for meat, hide, and ivory, accelerating their decline in areas where resources were already scarce. Yet, their disappearance was highly uneven. On isolated islands, mammoths survived for thousands of years after mainland populations vanished. On St. Paul Island, off the coast of Alaska, a small population persisted until about 5,600 years ago, eventually succumbing to freshwater shortages as rising sea levels shrank their territory. Even later, on Wrangel Island in the Arctic Ocean, a dwarf mammoth population survived until roughly 4,000 years ago. This staggered timeline shows that extinction can be a localized process driven by a combination of shifting climate, habitat loss, and human activity. At the limits of cosmic structure lies a physical state where gravity dominates completely. A black hole is a region of space-time curved so sharply by concentrated mass that its escape velocity exceeds the speed of light. The boundary marking this point of no return is the event horizon. These objects exist at two primary scales: stellar mass black holes, typically 5 to 80 times the mass of the Sun, and supermassive black holes, which contain millions to billions of solar masses at the centers of galaxies. Though black holes emit no light, 3 distinct lines of empirical evidence confirm their existence. First, stellar motions near galactic centers reveal their invisible presence. In our own galaxy, stars in the S cluster orbit an unseen object, Sagittarius, a star at speeds reaching several percent of the speed of light, indicating a mass of 4 million suns packed into a tiny volume. Second, the Laser Interferometer Gravitational Wave Observatory detects the physical stretching of space caused by merging stellar mass black holes, capturing these events as high-frequency gravitational wave signals. Third, in April 2019, the Event Horizon Telescope resolved the physical shadow of the supermassive black hole at the center of galaxy M87. By linking radio dishes across the globe, astronomers captured a bright ring of light bent by gravity around a dark central void, providing direct visual proof of an event horizon. The exploration of the cosmos transitioned from passive observation to physical contact during the Apollo program. While the missions are often remembered for their political and symbolic triumphs, they functioned as systematic, high-stakes scientific expeditions. Between 1969 and 1972, astronauts collected and returned 382 kilograms of lunar rocks, core samples, pebbles, and dust to Earth. These physical specimens redefined our understanding of planetary evolution. During Apollo 15, astronauts David Scott and James Irwin recovered a bright white specimen from the rim of Spur crater. This sample, designated 15,415 and famously dubbed the Genesis Rock, was identified as a Ferroan anorthosite. Radiometric dating revealed its age to be 4.46 billion years, making it nearly as old as the Moon itself. Because anorthosite is a light mineral that floats in heavy magma, its presence on the lunar surface confirmed the hypothesis that the infant Moon was once covered by a global magma ocean. Alongside these geological samples, the Apollo Lunar Surface Experiments packages established long-term monitoring stations on the Moon. The passive seismic experiment detected natural moonquakes, meteoroid impacts, and artificial seismic waves from spent spacecraft. These readings mapped the lunar interior, revealing a differentiated structure with a crust 34 to 43 kilometers thick, a solid mantle, and a small, partially molten core. Simultaneously, the Lunar Surface Magnetometer at the Hadley Rill site measured a localized surface magnetic field of 32 to 36 nanotesla. This unexpected level of crustal magnetism suggested that the early moon once possessed an active internal dynamo. By physically touching another world and leaving behind instruments to record its pulse, space science evolved from speculative modeling to concrete, evidence-based history. In the winter of 1995, Space Telescope Science Institute Director Robert Williams made a controversial decision. Overriding warnings from senior astronomer John Barcall, who feared wasting precious telescope time, Williams used his discretionary allocation to point the Hubble Space Telescope at a completely blank patch of sky near the Big Dipper for 10 consecutive days. The resulting image, the Hubble Deep Field, transformed astronomy. In a sliver of sky no larger than a grain of sand held at arm's length, the telescope captured several thousand distinct, fully formed galaxies drifting in the dark cosmic background. By extrapolating this single, crowded frame across the entire sky, scientists calculated that the observable universe, the portion of the cosmos close enough for its light to have reached us, holds hundreds of billions and potentially up to 2 trillion galaxies. Each of these massive systems contains hundreds of billions of stars, multiplying the planetary environments where life might take hold. By early 2026, astronomers had confirmed more than 6,000 exoplanets within our own galactic neighborhood. This vast catalogue reveals that planets are a common feature of the universe, not an anomaly. To locate potential biology among these worlds, astronomers map the habitable zone, the orbital band where temperatures allow liquid water to pool on a planet's surface. Yet this zone is merely a spatial guide, not a guarantee of habitability or the presence of life. The search relies on analyzing light filtering through alien atmospheres. Using transit spectroscopy and direct imaging, telescopes isolate the chemical signatures of gases like oxygen, methane, and nitrous oxide. However, interpreting these candidate biosignatures is complex, as non-biological processes can also generate them. The scientific demand for verification played out in September 2020. An international team reported detecting trace phosphine, a potential sign of anaerobic life in the highly acidic clouds of Venus. The claim triggered immediate global scrutiny. Subsequent observations by the Sophia Airborne Observatory and the Venus Express spacecraft failed to find the gas, ultimately setting strict upper limits below 0.1 parts per billion. This rapid self-correction illustrated the danger of false positives and the necessity of exhaustive planetary context. Equations like the Drake formula serve as conceptual prompts to structure questions, but they offer no predictive power. For now, the step from cosmic abundance to biological certainty remains an open frontier. The technology to find answers is still being built, leaving the question of our place in the cosmos, waiting for the next generation of observers to look up, ask what comes next, and keep searching. We now stand on the edge of the cosmic ocean, scanning distant worlds for the faintest breath of life. Yet our history reminds us how fragile planetary survival truly is. The ultimate question is no longer where we came from, but how long we will endure to keep looking. After all, we are the universe's way of knowing itself. What do you think lies ahead? Share your thoughts below.